Today we will read how to design the combination circuits, but before that first I want to discuss the previous day's quiz question. There was only one question, and that was that using D as the MEV, that reduce the function Z equal to a dash b dash c dash d plus a dash b c dash d dash plus a dash b c dash d plus a b dash c dash d dash plus a b dash c d dash plus a b dash c d plus a b c dash. Now, that last day we have discussed the map entered variable. That means that if this is a technique that which reduces the larger number of variables towards the lower one. So, here the z function is a 4 variable function, a b c d, there are 4 variables. So, now we can rearrange this function like that. See, the first min term a dash b dash c dash d is as it is. Now, that a dash b c dash, a dash b, that means the second term, and a dash b c dash d means the third term. We take the a dash b c dash common, then it will be d plus d dash. Now, a b dash c dash d dash means the fourth min term, this is a b dash c d dash fifth min term, and similarly the from the sixth and the seventh min term we take, or we can write the sixth and seventh together by taking a b dash c common into d plus d dash. Now, if we use the normal K map, then as it is a 4 variable, then it should be a 4 by 4, means 16 min terms should be there, maximum possible 16 min terms. Now, we are reducing 1 and we are taking D as the MEV, that means that map entered variable. So, that it becomes now 3 variable A, B, C. So, how we will be doing that thing? See that this is the K map for 3 variable, and here this is for A B, the 2 variables, and this is for C. So, we can write the thing that see that A dash B dash C dash D. So, the first one is A dash B dash C dash. So, I can write the element, first element as D. Similarly, the second thing, the second min term now A dash B C dash. So, A dash B C dash and both D plus D dash are there. There is no min term for A B C dash. So, it is 0. Now, again A B dash C dash, the fourth one, it is the term is D dash. So, I write D dash here. Now, A B C D dash. So, A B C D dash, this is the second row, third column. This is A B C D dash. So, A B C, the D dash I put here, and the second row, fourth column, A B dash C into D plus D dash. So, I put D plus D dash here. Now, if we try to select the couple the same way that we have done in the K map, because our aim is to reduce the function. So, how we can do that thing? See here, these are 2 adjacent elements where other than 0 value exist. In normal K map 1 was there. Now, see here both D and D plus D, D and D dash exist. Here one D is there. So, I can put a couple here by doing D and D dash, but here D plus D dash itself will make a couple. Similarly, here D plus D dash itself will make a couple, but then adjacent D dash, this adjacent D dash will make a couple with this D dash. Similarly, here this D dash will make a couple with this D dash. So, now I can got 1, 2, 3, 4, 5 such couples, where the one element itself, there are 2 such elements, the D plus D dash, which makes some reduction. Now, we see. So, if now we do that thing, see reduced function will be A dash C dash D dash. How this is A dash C dash D dash? See, when we will be taking this couple, that this D and adjacent D, then this becomes A dash C dash D. So, this couple is A dash C dash D. Now, this reduces to, this one reduces to A dash B C dash, because D plus D dash is 1. So, A dash B C dash. Similarly, that this one reduces to A B dash C. This, okay, not this one. This one will make a couple with this D dash, and they will form D dash. So, this will be A B C A C D dash, and these will form, this one and this one will form, because they are in same column. So, A B dash D dash. So, 1, 2, 3, 4, 5, this will be the reduced function. And see, this is the A dash C dash D dash, A dash B C dash, A C D dash, A B dash D dash plus A B dash C, this are the reduced function. Now, we start the combinational circuit design. First, we recapitulate some of the traditional method of function realization. Already we have discussed that the Carnot map, that means given a table or the some expression, Boolean expression, from there how we can reduce that thing, then how we can realize that functions. Now, normally that any circuit can be realized by 3 gates, AND, OR and NOT, and these are same as that of our 3 operators, that dot, plus and the inversion or the complement. Now, a NAND or NOR gate can be used as an inverter, because already we have discussed that NAND is nothing but the NAND is, we can write like that, say this is a 2 input NAND, which is a 2 input AND followed by a inverter NOT. Similarly, that NOR, this is a 2 input NOR that can be replaced by 2 input OR followed by a inverter. So, always the NOT can be replaced by NAND and NOR. Now, it is convenient to construct functions requiring larger number of inputs with 2 or 3 input gates. What does it mean? Say I have 4 input AND gate. Say I have some 4 input AND gate. What I can do, that I can make a 2 input AND gate, another 2 input AND gate. Say these are A, B, C, D, 4 inputs. Now, these are 2 inputs A, B, these are 2 inputs C, D, and again I can put another AND gate here. So, this will be F equal to A dot, B dot, C dot, D, and here it is A dot B. Say this is F1, say this line is F2 equal to C dot D, and this is F equal to F1 dot F2 means A dot B dot C dot D. Similarly, the same thing will happen for OR or other operations also. Now, the XOR and the XNOR gates can sometimes be used to reduce chip count over conventional gate implementation. So, what are the XOR and XNOR circuits? Say XOR circuits where the notation is like that. So, this is a 2 input XOR A B and F, where F is A B dash plus A dash B. Now, similarly, XNOR is say 2 input, then XOR 1 NOT is there, and again if it is a 2 input AND gate. So, F is actually A, normally we give XOR notation is like that. So, A XOR B complement, and this is A B dash plus A dash B, and this becomes, if we apply the De Morgan's law, then it becomes A B plus A dash B dash. So, these two sometimes the function are realized by employing only these two gates, XOR and XNOR. Now, there is some design procedure. See, first we are normally the combination circuits, the concept is very simple. See, here the combination circuit means, say this is one functions or the circuit to be realized. Just we are considering as if this is a black box. This is a set of inputs, and these are a set of outputs. So, these are inputs, these are outputs. these are my circuit, or what I can tell, this is a set of functions realized by gates. Now, here this function, combination circuit means this function or the output behavior, the outputs are only depends on the inputs. This set of outputs depend on the set of inputs. Now, how to design these combination circuits? So, first we see a simple design procedure. So, the first step is determine the goals of the system for a given problem specification. Means given a problem, first we will decide that what will be the output of the system, what we have to compute or we have to determine. Then second is that draw a block diagram showing all possible input and output lines. Identify the different function of the system by separate block or functional module. Now, say just now I mentioned this, if I explain the second point, see we have, this is a block diagram level. There are set of inputs and set of outputs. Now, see that this is a function f realized. Now, this f can be a large circuit, or just now I mentioned that this is a set of functions. See, this can be a set of functions f1, f2, f3 like that. Now, what we can do, that as if these we can identify as separate blocks, but the primary inputs or the inputs are same. Say it may happen that this I1, say inputs are, say input there are m inputs and say these are I1, I2 to Im. Similarly, the outputs are O1, O2, say On, n number of outputs. That means m inputs and n outputs. Now, say same, say as if I1, I2 are fed to F1, whereas say some I3 or Im that is fed to F3, or one can be fed to F2, some other can be fed to F4 like that. Similarly, the outputs can be. So, the original function is partitioned into smaller modules and identify that blocks, and there are separate functional module. Now, the third step is express the relationship of each output variable to the input variables by table or by equations. Now, what we are doing that for the whole function, now for the each smaller module, what we can do, we that express the output variable to the input variables, because truth table is nothing but all possible input output combinations, or the all set of equations if we consider, that means for set of equations for all functional modules f1 to fn, then they will actually constitute the whole system. So, we will now express the relationship of the output variable to the input variables. Then we will construct the truth tables for all possible outputs and reduce output variable expression to its simplest form. Already we have discussed how we can reduce that thing. So, using any one of the method we can reduce that expression. Now, check for any necessary hazard covers and modify the reduced expressions if necessary. Now, we will see whether my expressions or the set of expressions reduced, whether there are some static hazards or dynamic hazards exist or not. Then the last day the method we discussed, by introducing the redundant implicant we can remove the hazards. So, we will modify, that is why that we have to modify the reduced expression if necessary, means if the hazards are there. Now, we have a set of equations and reduced equations and then implement the circuits eliminating and redundant gates. So, this is overall the simple design procedure. Now, one by one we will see. Now, first we see a combinational function generator. Say a circuit is required to produce jet for various combinations of the ABC. Means, say I am taking one black box, as if this is my system. There are 3 inputs and 1 output. See, inputs are A, B, C and output is Z. Now, first I have to see that what the function it realizes, or what is the input output relationship. Now, expressing input output relationship by table. So, here one table is given which actually gives that if the ABC inputs are, they take these values, then what will be the output. So, this is one table. If it is 0 0 0, then output is 0. If it is 0 0 1, output is 1. Similarly, if it is 1 0 1, then A equal to 1, B equal to 0, C equal to 1, then the output Z is 0. So, this we have identified that this is the relationship, that means output will be produced if the inputs takes this particular values. Now, from this truth table we can easily draw the Carnot map. As this is a 3 variable function, because the inputs are 3. So, we write that these 3 variables are A, B, C, and see from the previous table that say for 0 0 0 it is 0. So, there are 1 2 for 0 1 1 combination output is 0. For 1 0 1 means 0, this is 3, this is 4 and or 0 3 5 6. For this 4 combinations of these 4 inputs, the output is 0. See that is for 0 0 0 0 means 0. This is 3, this is my 5 and this is 6. So, there are 4 zeros and rest are 1, that means there are 4 ones. Now, if we reduce this expression, then we will get that Z is A dash B C dash plus A dash B C plus A B C plus A B dash C. Actually, there is no reduction possible. Here there is no reduction possible. Mainly we have the mean terms we have written. So, now if I want to realize these circuits, what will be the type of circuits? See, there are 5 gates are needed for the design. Now, we are assuming that the variables and complemented as well as uncomplemented variables are available. So, if we draw that this type of circuits, there are 4 AND gate, there will be 4 AND gate and all are 3 inputs. Here it is A dash B C dash, this is A dash B dash C, this is my A B C, this is my A B dash C dash, and these are the, and now these are sum of product forms. So, this is OR and this will give my Z. So, there are 4 gates needed, 4 number of 3 input AND gates, these are the 4 number of 3 input AND gates, and 1 OR gate, 1 4 input OR gate. Now, typically or traditionally what we can do, instead of this 3 input AND gate, we can take 2 input AND gate. Instead of this 4 input OR gate, we can take 2 input OR gate followed by another 2 input OR gate. That means, always this 4 input OR gate, as already I mentioned, this can be realized 2 input OR gate and again that will be another. So, this will be the same thing. Now, already we have seen from the Carnot map that there was no reduction possible, but we can realize the circuit because now we are discussing how the expressions or the functions are realized by the gates. So, even the reduction is not possible, but see this particular expression I can take some common terms or literal. Say from the first 2 terms, see from the first 2 terms A dash B C dash and A dash B dash C. From here, see I can take A dash common. So, this is B C dash plus B dash C. Similarly, the last 2 terms I can take A common and this is B C dash plus B dash C. Now, what is my B C dash? B C dash plus B dash C? This is nothing but B XOR C. So, this is my B XOR C. So, this is X. So, how this expression becomes? Then Z equal to A dash X and here this is A. What is this term? B C dash plus B dash C dash. This is nothing but X NOR already we have seen that this is x naught, that this is, that means this is my x dash, that B C plus B dash C dash. So, here B C dash will not be there, this is B C plus B dash C dash, this is B C plus B dash C dash. Now, this is my x dash. Now, A dash x plus A x dash, which is A x or, which is A x or x, that means again I can take one and A and x, and this is my z. So, this is my A x or, this expression becomes A x or x. So, A x or, and this is my x means B x or C. So, x is, this is my x, B x or C. So, the same function I can realize by this circuit. See that this is my B x or C. So, this is my x equal to B x or C, or we can give a different notation. Now, conventionally we use this thing, that B x or C, and this is my z is again A x or x, means A x or B x or C. Now, see, if I use only XOR, then instead of that 5 AND OR gates that initially we have seen, the 5 AND OR gates we have realized there, here only 2 XOR gates are needed. So, this can be a circuit realization of that particular circuit function. Now, we consider a bigger example. Now, say this is a comparator design. The problem statement first we tell, the design a binary number comparator that accepts two numbers A and B of 2 bit long and compares the numerical values of these numbers. So, if I draw that, it will be, say, this is a system, or that my comparator, there will be 2 inputs, 2 bit. So, this is my, say, A1, A0, okay, and another 2 bit, say, B1, B0. So, these are the 2 bits, 2 input AB, each has 2 bits. Then output will be only one, it will tell whether A greater than B, we are telling this is as a greater, then A equal to B, and whether A less than B. So, this is my comparator. So, this we are telling EQ, this we are telling LS. So, this is my greater. So, two inputs and one output, 1 bit. So, this we have to design, this is my comparator. Now, again first we try to identify the output input relationship. See that here there are two, we have defined two inputs, and they are see this is one of the inputs A, this is another input B, both has 2 bits. So, as if we are thinking there are 4 variables A0, A1, B0, B1. Now, we take all possible combinations because they are the inputs. So, all possible combinations of the 4 inputs, and we see that what will be the output, means mainly we are trying to identify the output input relationship. See that these are A1 A0 is 0 0, B1 B0 is 0 0, the numerical value is 0. So, these are equal. So, that is why this is a 1, and greater and less than they are all 0. Now, what we can do then, that instead of designing one output, what we can do, we can this type of thing also we can do, that A B C, A not A B C, that A0 say A0 A1 means A1 A0 B1 B0, there are 4 inputs, I can make 3 output, one is greater, equal and less, that also we can do, and this is my comparator. This is my comparator. So, when see that 0 0, A1 A0 is 0 0 and B1 B0 is 0 1. So, what is the numerical value AB has? See, this is 0 0 means this is 0 value, this is 0 1 means 1 value. So, A is less than B. So, that is why LS is producing a 1, whereas the GR line and the EQ line means greater and equal, they are giving 0. Similarly, we take this one, so 0 1 0 0. So, 0 1 0 0, see this 0 1, this is 1, this is 0. So, it is A greater than B. So, this greater than is giving a 1, equal is giving a 0 and less than is giving a 0. So, for all such conditions, now say the next one 0 1 0 1, 0 1 0 1, this is 2, the value is 1, 0 1 the value is 1. So, A equal to B means my EQ line means equal, that will produce a 1, that means equal, it is true, and whereas the greater and the lesser they are false, means they are producing a 0. So, in this way we have put the what output line, the 3 output lines will generate the value depending on the a particular combination of the 4 inputs. So, this is the whole combination or the all possible inputs combinations are there, and for them what output values should be generated by the system, that is given. Again for these all one values, these are, this value is, A value is 3, B value is 3. So, A equal to B, and so EQ is 1, whereas greater GR line and LS lines they are 0. So, these truth tables are given. Now, the already we have discussed when that design procedures I told. See, as if here there is one comparator function, f. Say I am writing one comparator function f, and there are 4 inputs A1, A0, B1, B0. There are 3 outputs GR, EQ and LS. Now, I can replace or identify the subblocks or submodules, means this F I have as if partitioned into 3, the F1, F2 and F3, and say this is producing say GR, F2 is producing say EQ and this producing a LS. Say as if all inputs are fed to all the modules. This is the situation, and now this F1, F2, F3 we have to design. So, what we can do now, as if this we are partitioning this as a 3 sub problems. Actually, there are 4 inputs and 3 outputs, as if we are partitioning 4 input, F1 as 4 input 1 output, F2 as 4 input 1 output and F3 as, that means if we take this one. So, this my, I can break, this is my F1 and this is GR. I can break F2, output is EQ. Then I can break F3, output is LS. This. Now, these 3 functions I have to design. Now, say for output GR. Now, again we have to revisit that truth table, that means for which min terms the output is 1 and for which min terms the output is 0. So, now we will consider or we concentrate only on the GR. Now, see for the decimal value, if we write for 0, 1, 2, 3, then 5, 6, 7, except 4. So, for 4 it is, for 4 it is generating a 1. Similarly, for 8 it is generating a 1, 9 it is generating a 1, then 12 it is generating a 1, 13 it is generating a 1, 14 it is generating a 1. Okay. So, 4 4 8 9 12 13 14. Now we see this is, if I draw the Carnot map, see this is 0 0 0 1, actually this is 0 1 0 0. So, this is my 4. Then this is 1 1 0 0, means this is 12, this is 8, then 13, 1 0 0 1 means 9, 1 1 1 0 means 14. So, 4 8 9 12 13 14. So, for this it is giving a just again we check that if it is 4 8 9 12 13 14. So, this is the mean terms of 1. So, now if we the same thing we see for LS, that see that A1 A0 is 0 0, B1 B0 is 0 1. So, this is less. So, that means here it is, this is a lesser value, A is less than B. So, this is my 1. Again 1 0, 1 0 is less than 1 1, means 2 is less than 3. So, this is 1 0 1 1 means 11, and similarly 0 0 is less than 1 1, 0 0 is less than 1 0, 0 1 is less than 1 1. Now, 0 1 1 1 means 8 4 or 4 2 1, this is 7 and this is 6. So, for 1 3 1 2 3 6 7 11, for these values are less. Now, similarly we can write that equal also. See, for LS, now if we see that this is for greater 0 1, greater than 0 0, already we have seen these are greater. Similarly, we can draw that equal also. Now, if we write the expressions for that 3 Carnot maps, now if we write the expressions for GR, EQ and LS, they are reduced to GR is A1 B1 dash, A0 B1 dash B0 dash, A1 A0 B0. Similarly, EQ will be A1 dash A0 dash B1 dash B0 dash, A1 dash A0 B1 dash B0, A1 A0 B1 B0 plus A1 A0 dash B1 B0 dash, and this is equal to A1 B1 plus A1 dash B1 dash A0 B0 plus A0 dash B0 dash, and the LS line means less than line will be A1 dash B1, A1 dash A0 dash B0 plus A0 dash B1 B0. So, what we can do now, if we want to realize these circuits, see for that, first we see that for that equal line. So, equal line, this is A1 XOR B1 and A0 XOR B0, and then they are ANDed, means that this will be, this is a A1 XOR B1, this is A0 XOR B0, and then it will be my equal line. Similarly, the LS line will be that mainly the realized by the AND OR circuits, and the GL line will be AND OR and realization by the AND OR XORs. So, in this way we can design a combination circuits. Now, we see that the previous thing, see that if we, this is one type of realization where mainly the AND, OR and the XOR, these are the three gates we have employed, we have used. Now, if we study this greater, equal and less than line, then we will be seeing that this the greater line will be less complement of the less than and the equal line. That means that if we again see that circuit, that here that three separate, the outputs are that, see here the outputs are, three outputs are designed separately. Instead of that, what we can do, that if the LS and equal, these two are designed, say LS, once the LS and EQ, these two outputs are realized, then as if we can reuse this, or we can use these two outputs, and this is OR, and then actually this is a NOR, OR, and then we can inverted that thing, which will give the greater line. So, this is that GR is EQ plus LS complement. So, this can be, in this way we can again still reduce that GR circuits, and see mainly this thing has been done here, that LS and EQ, and this is by XORing that thing. So, in this way, that first we have to from the problem specification, we have to set our goals, that what we have to determine, that means the outputs. Then the relation, we have to identify the relation between the output and inputs. Then we can deduce the expressions, and using some Carnot maps we can reduce the expression sets. Then from that set of reduced expression we can realize the gates. Now, again the realization can be of different type. Just now what we have discussed, that can be simple AND or XOR XNOR circuits, or that can be a different type of realization possible. Again we will discuss further. So, today's quiz is just design a combination circuit that performs the addition of two bits called half adder. That means, the previous carry bit is not considered, only that there are two operands A and B, and we know the addition operator, then we have to design a combination circuit which does this operation. So, this is the quiz for this lecture. Thank you. In the last class, we have read that how we can design the combination circuits. What is the conventional design procedure, and we have seen a comparator design. Now, today we will see how the common circuits, such as some very popular circuits and very important circuits, that adder, the different type of adders can be designed, because these adders are nothing but the combinational one. So, as its name implies, the addition consists of the adder does the addition operator, and this consists of 4 possible elementary operations, and these operations are say there are 2 bits. Say this is what we have shown, that for each type of adder, half adder and full adder, a number of different type of realization is possible, and mainly depending on the application, that means whether we want to reduce the area or we want to reduce the power, that we will select that type of realization consisting of AND OR gates or XOR gates or the NOT gates, etc. Okay. Now, today's this quiz question is, again this is a combinational circuit design and very similar type, that we have discussed the adder, and now the problem is design a combination circuit that performs a subtraction of 2 bits, mainly the addition we have discussed and the subtraction. For similar to the half adder and full adder, first we have to do the half subtractor and then it is a full subtractor. So, first we have to define what do we mean by half subtractor. Half subtractor means that again this will be a single bit minus, where that previous borrow bit, where for addition it was the carry bit and now it is a borrow bit, that is not considered, and for full subtractor the 2 operands as well as the borrow bit from the previous subtraction should be considered. So, these are the quiz question for this current lecture. Okay, thank you.